is a long-standing supporter of Cambridge Spark. Almost 2 years ago, I think. It's the first time you came to one of our bootcamp to give a talk to our students. So Miriam has worked for Yahoo Research, the Bell Lab in Cambridge, and recently joined the Wikimedia Foundation. So has a breadth of experience on doing research in an industry setting. So look forward to your talk.
Thank you. So good morning, everybody. Thank you very much for being here. I'm very happy to be supporting these programs because they're very interesting. So yes, my name is Miriam. I'm from the Wikimedia Foundation. I'm a researcher there. The Wikimedia Foundation is the foundation behind Wikipedia and all the other projects. So I recently joined 3 weeks ago. It's very exciting. But because I recently joined, whatever you're going to see today is basically my past work outside the foundation in the past 4 years. So my background is computer vision, which, as you might know, is that branch of artificial intelligence that analyzes and understands images at scale. And what we're going to see today, actually the title on the sheet is different, but it's fine, is how we can make these machine vision frameworks both subjective and a bit responsible. This is a pretty much useless slide about me. I just like to travel a lot, live in different places, and do beautiful research around the world. Let's get to the topic. Computer vision. So computer vision, as you might know, provide tools that, given an image, are able to detect visible, tangible objects, everything with a shape. So things like faces and the identity of the person depicted, objects and the scene where the image has been shot, and it does so with an impressive accuracy thanks to recent developments in deep learning that we are all aware of. And so detecting these tangible objects works very well, and it's very important. However, if you think about it, when we look at an image, we don't only see what is directly visible, right? So there is this whole world of intangible properties that we necessarily attach to an image when we look at it, but we can't really see their shape. Things like the beauty of the image or the sentiment of the image. I can say this image makes me happy, but I won't see the shape of sentiment as I see the oval shape of a face, right? And so detecting this subjective shapeless properties is not an obvious task for traditional computer vision framework. So what I like to do in my research is to design these subjective machine vision frameworks that essentially break the boundaries of computer vision, embracing disciplines far, far away from computer science, and effectively, given an image, can detect subjective properties, perceptual properties such as the beauty, the sentiment, or the creativity of the image. So this is more or less what I do, and the problem when you do this kind of strange things is that because the properties you're trying to quantify are not really objective or binary properties, you really have to carefully design these technologies because these models replicate human perception, and therefore they carry the human bias with them, right? So you don't want these algorithms to be biased, and you really want these subjective models to be actually subjective, so to represent the diversity of tastes of the multicultural world where we are in. And what I call, how I define the subjective machine vision type of technologies that I like to develop together with my colleague is a bit responsible, because it's both trying to be unbiased and also trying to be representative. So in the next few slides, I'm going to show you 2 examples of what all this means, of what is actually subjective machine vision and how can we make it a bit responsible. So the first example is from the field of computational aesthetics. What we do as scientists in computational aesthetics is that we design models that, given an image, are able to automatically score it in terms of aesthetic appeal, or the photographic beauty, or the photographic quality, and so on. And so actually the example I want to show you is on computational aesthetic, but on a specific image domain, which is the domain of portraits, so images with faces only. So we wanted to design this computational portrait aesthetic framework that, given an image of a face with a face is able to automatically score it in terms of photographic quality. Now, the important thing of this framework is that we don't want to score the face in terms of beauty. We don't want that. We just want to score the image composition in terms of beauty, knowing that there is a person in it. And the reason why we want a specific framework for faces is because portrait photography is a separate branch of photography, and when you take pictures of people, you really need to follow specific portrait photography rules to convey the subject humanity. And so that's why we also need a computational version of that. And so what we actually do is that from a bunch of images annotated, of portraits annotated with photographic quality score, we actually dig into portrait photography literature, and we map each of the rules that photographers follow to shoot good portraits into a visual feature, so into a set of numbers describing some property, some photographic property of the image. Let me just give you an example of what this means in practice. So one of the most important properties of a portrait is the sharpness of the eyes of the subject, because this gives you a sense of realism of the picture. And so how do you actually automatically extract this information from the image? It's actually fairly easy. You take an image of a portrait, you pass it through a neural network that gives you that region of the image where the eye lies. And then from that region, you use some signal processing to extract the edges of the image. And then the higher the values of the edges, the sharpest the eye area will be. And so this is how we automatically quantify one important property, such as eye sharpness, for example. So we have actually a bunch of them. I can't describe them all, but you know, you have all the annotations, you have all these visual features. You can use them in a machine learning framework that accurately predict the portrait beauty. It's fine, it works. But what we actually want to see is whether our algorithm is biased or not, whether it's stereotyping or not on the subject, because we don't want that, right? And so what we do is that we look at how the machine behaves when assigning good and bad portrait score. And what we find is there are some features, such as the landmark sharpness, the face landmark sharpness, that are positively related to the portrait beauty. And this makes sense if you kind of know a bit of portrait photography. This makes sense. Also the difference, so the contrast between the foreground and the background. There are some features that are negatively related, and there are some features that actually do not correlate at all with portrait beauty. And these are the demographics features. So this tells us that no matter the age, the gender, or the race of the person depicted, if the photographer does a good job, then according to the algorithm, the portrait will be of high quality or not. And this is exactly what we want to see. So we wanted to check that the algorithm was not biasing. And this was only possible because we designed interpretable features, and we did this kind of deeper analysis. Okay, and so the second example of subjective machine vision I'd like to show you is from a project that we started some years ago with a bunch of researchers from all around the world. So the aim of the project was to design a image sentiment detector. So a machine learning framework that given an image can tell us automatically the sentiment that the image aroused. It's happy, sad, etc. And so because we were actually a bunch of people from all around the world, we soon realized that we couldn't flatten one single notion of sentiment into a machine. And so what actually came out from this project was an entire framework to study, from a computational perspective, the impact of culture in visual emotion perception. And so not only we have culture-specific sentiment detectors for images, but also we created this entire fabric for researchers from different fields to actually analyze the relationship between culture and sentiment from a computational perspective. And so obviously, because we are dealing with machine, the first step was to collect a lot of data. And so we we collected this large data set of around 8 million Flickr images. And each image, I'm going to skip the details of how, but is annotated with a sentiment dimension, so a positive, negative sentiment value, and a cultural dimension, which is the language of the users who uploaded the picture. It's a proxy, but this is the best that we could do. And so with this bunch of data, we can actually run some interesting shallow analysis. And so, for example, we run a deep learning-based face detector, and we separate images of faces with images from images without faces, and we found that, for example, across culture, no matter the culture, images with faces carry a more positive or more polarized sentiment in general, no matter the culture. And then we find also some culture-specific elements. So there are some visual elements that only a single culture in our data set assign to emotion. And because I'm half Italian, I just want to mention that the only language community in Flickr having tax evasion as a concept related to emotion is the Italian language community, which makes sense if you're Italian or if you know Italians. So we have a bunch of them. So what we actually see, this is a joke, but we actually see by analyzing this data that there is a lot of variability of how different culture assign meanings to emotion, visual meanings to emotion. And so this motivates us to actually design these culture-specific sentiment detectors. So what we do is that we take we take all the images from a given culture, and we design this very simple deep learning framework that, given an image, learns how to replicate, given an image of a given culture, learns how to replicate how that culture assigns sentiments to images. And so the nice thing about this is, because we do this with a lot of different cultures, is that now, given an image, we also have a nice demo. We can automatically score it according to the Chinese sentiment or the Italian sentiment or the French sentiment and so on. And so because also we are researchers, we can't just stop there and say, hey, we found these detectors. We want to also understand whether they make sense and whether they can tell us something more. So what we do is that we compare the sentiment model. We compare somehow the underlying data distribution of these models, right? And what we find is that, for example, among the language communities we consider, the Chinese sentiment model tend to be the most different compared to all the others, while the sentiment models from Latin culture, so Italian, French, and Spanish, tend to be very similar. This tells us that, according to our data, Italian, French, and Spanish tend to have the same way of expressing visual emotion compared to the other language community, which might make sense, and it kind of validates the whole process that we went through. Okay, and so before talking about application, because Raul told me the team is data science in practice, right? So there is a section about applications of all this, but there is an in-between section that I would call it like, don't try this at home. It's essentially a story of how research work cannot be directly implemented into real applications, and that there is, so the path towards testing research models in the wild is a bit bumpy, right? So it's not like straightforward. We can do a lot of beautiful research, and I love doing research, but when you go through the application side, and I know it as an industry researcher, you really have to be careful about the data that you are analyzing and the entire user experience. So again, this story is about computational aesthetics. So when I was working for a big internet company, everybody was super excited about having computational aesthetic model for image search, because of course you want to retrieve not only images of cats, but beautiful images of cats. And so we had this super beautiful computational aesthetic model trained on neural network, trained on whatever you want, that they were trained on research data set for computational aesthetic, they're very big, but they're very much coming from professional photographers. So our models were working very well, and then we applied them in the wild, and this is what happens. These are the best images of the wild web, more or less according to, actually this is even good compared to what I was saying, according to the models trained on professional image data sets, right? And this is because we didn't really, at that time it was probably a bit early times of computational aesthetic, so we didn't really understand the intrinsic differences between professional images that we were using for research and the wild web images, that they are really very different, right? So first of all, web images are nothing but professional, so the quality is very much skewed to the bad side. And also, web images are not only photographic, so there is a lot of illustration, clip art, and so on. And so, of course, we didn't have these images in our dataset. And so again, because we are researchers, we did a research project out of this problem. And basically, we had two research questions in mind. First, can we systematically quantify the differences between these professional images and the images in the wild web? And second, can we actually come up with a solution to effectively score images in the wild web in terms of beauty, possibly reusing some professional image knowledge? And so we collected this large data set of web images annotated according to the aesthetic degrees by professional editors. And then to answer the first question, to understand differences, you can't see much, sorry, the differences between web and professional images, we actually did we actually extracted from these two groups of images, web and professional, a bunch of these computational aesthetic features, so sharpness, colors, etc. And then we correlate each feature with the beauty of the image. And by doing so, we can understand what are the features that make web image beautiful and what are the features that make professional images beautiful. And we have a lot of findings there, but essentially my computer stopped working, but I'm gonna, it's dying. But I'm gonna talk, and then if it goes back to life, I go on. Anyway, so what we found is that the meaning of each features, the meaning of a feature changes from web to professional images, and that actually the feature boundaries are very, very different. And I'm sorry, I don't know what. Okay, we're back. So what I was saying is that, just to recap, sorry about that. So that what we found is that the meaning of a photographic rule for professional image and the meaning of the same photographic rule from web image is very different. So let me talk about sharpness again. Sharpness, again, is one of the most important properties of professional images. So generally, the sharpest the foreground subject is, the better it is. So if a model learns this association, then you go in the web and you retrieve the sharpest images in the web, which are very sharp, right? But they're just textures, sharp textures, they're not exactly the highest quality images we've found. So we have a lot of these findings, and so we actually now can live in peace and understand that these two data sets are different, so we can now come up with a solution for that. What we did is that we designed a fully convolutional neural network specifically designed for scoring beauty. So with three outputs, one for low, one for medium, and one for high beauty. And then we train it in various ways, one with professional images, one with from scratch with web images, and one trained on professional images and fine-tuned on web images. And what we actually find, I'm going to skip all the details of this plot, is that the best way to actually score web images is to reuse some knowledge, so to transfer some knowledge from professional images to web images, and so to fine-tune the network from professional images to web images. And this is because by training on professional images, the network learns the actual photographic rules, and then you just adjust these photographic rules by fine-tuning on web images. Okay, and now that we learned these lessons, we can actually talk for I don't know how many minutes I have now, but as much as I can about the applications. Why do we care about doing all this apart from publishing nice papers? There are actually a number of nice applications where subjective machine vision can help users have a better experience. So the first one is video browsing. So if you think about a video browsing platform, if you think about how what drives you clicking on a video or another, it's definitely the title, but also the thumbnail. So that frames that should represent the video, right? That frames that is visualized on top of the video. And so what happens is that this frame not only has to be representative of the content of the video, it also has to be attractive because it should attract the attention of the user. And so we designed this automatic thumbnail selection system fully based on computer vision that, given all the frames in a video, automatically selects that single one that should become the thumbnail. And according not only to the content, to how much it represents the content of the video, but also according to how attractive the frame is. And obviously to do that, we used subjective machine vision. We ingested in the model, and we saw that users were kind of happier when you had this subjective bit in the system. The second application is obviously advertising. I've been working some years in computational advertising, yes. And so, as you can imagine, ads, as you know, I guess ads are multimodal items in nature. So ads get clicked not only because of the text, but also because of the attractiveness or the pleasantness of the image. And so we designed this advertising quality framework that would automatically separate pleasant ads from non-pleasant ads, especially because we want to discard non-pleasant ads from the stream. And there were obviously a lot of textual features, but also a lot of subjective machine vision to make sure that we were effectively scoring the pleasantness of the image of the ad. And the second application, it's still in advertising, is about mobile advertising. Briefly, we designed in this project, so we did this project in which we wanted to automatically detect the pleasantness and the degree of mobile friendliness of advertising landing pages in mobile advertising. And so what we did is that we extracted obviously a bunch of features from the HTML and from the code and from the CSS, but also we used subjective machine vision framework on the screenshot of the landing pages. And with that, we saw that we could improve both obviously the detection of aesthetically appealing landing pages, but also of the mobile friendly, of the degree of mobile friendliness of landing pages. And the last application, I think this is my favorite, is about photo sharing platforms. I've been working a lot in photo sharing platforms like Flickr, for example. Photo sharing platforms have millions of users and billions of pictures. And they are a fantastic space with a lot of very good photographers. And however, what happens in photo sharing platforms is that only a tiny portion of images is actually visible to normal users. And these are, in general, the most popular images because popular images spread easily around the network, they get retrieved more easily, and so on. And so this is a very traditional dynamic and obviously makes user happy because in general, popular content in photo sharing platform is also of pretty high quality. But this is kind of forgetting all the good photographers are out there that do not have social attention. So there might be some very good photographers that are non-popular and that they don't get the exposure they deserve. And so together with my colleague, we thought, why don't we employ a computational aesthetic framework that automatically scores all the images in the platform according to intrinsic quality, and then we can use this intrinsic quality metric as the main driver to surface interesting content. And by doing so, we do not only make users happy because they see beautiful content, but also promote those photographers that need attention because they're good, but they are not social enough to get to get the right attention. And so we did a bunch of tests on this, and one of these was, for example, scoring a bunch of non-popular images in terms of beauty, ranking them according to the predicted beauty, and then ask crowdsourcing contributors to tell us to annotate the beauty of these surface pictures. And we were very happy to see that these surface gems from non-popular photographers were considered as beautiful or even more beautiful than the most popular Flickr pictures. And also we were very happy to discover these hidden gems that we wouldn't see if we didn't have some subjective machine vision framework surfacing them for us. This work is going on. This is a recently published paper in which we wanted to see whether computational aesthetic models embedded in photo sharing platform are useful just to surface good photographers, or there is something else. So we did this kind of natural experiment where we look at the effect on a user with a certain average beauty in his pictures. So the effect of him becoming friends with good photographers. So with users whose average beauty is higher than average, okay? And so what we found is that beauty fosters beauty. So if I become friends with photographers who are better than me, I tend in time to become a better photographer. And so this is an early work, is recently published, but I think it's a nice message that we might at some point consider to spread high quality content in this way. And so with this, I conclude just a final remark. So basically with all these findings, I hope kind of show you how computer vision and subjective machine vision can not only help us understanding how we perceive the visual world, but can also empower technologies with tools to surface content to users that make them feel well, and that actually and promote more high quality content in photo sharing platforms. And with that I conclude. I thank you very much, and all these people, because I didn't do all this work alone. This is all my collaborators, and thank you very much.
Amazing. We've got time for two questions.
So sorry, I went. Yep.
So when you were talking about the sort of language for culture, was language synonymous enough with culture? Because you can imagine things like sort of English, but then if you've got Americans and UK, there could be quite some cultural differences there.
Absolutely. This is a major limitation. So actually, in a lot of the experiments that we did, we use only country-specific languages, such as, for example, Italian or German. But definitely, this is a limitation. But so in order to get such a diversity of culture, really the data was becoming very, very granular, because you have to match language and location. But then location, I mean, I live in London and I write in English, but I'm definitely not from London, right? So it becomes very difficult to do it in a fully automatic way, so it requires a bit more curation. But still, we had some pretty nice findings, and this is an initial effort towards a fully multicultural subjective machine vision, but this is definitely one of the major drawbacks. Yeah. Yeah.
Any final question? I'm actually curious, is there any photographers in the room that does that as a profession? There's one of them right there. I'm just curious if an application of that could be, I presume you're looking at improving your photography over time.
Yeah, so I was actually thinking, I wonder if an application could be, probably going to say the same thing, in terms of photography training, seeing how your learning curve is progressing and sort of having an objective measure to compare yourself against as you develop into a better photographer. That could be super interesting if you looked at anything like that.
Not really, but this is, so the last experiment I showed kind of goes a bit in that direction. So it's not really an objective measure, it's a bit more, so you're comparing to yourself. And you have this, you have your average beauty at time t0, and then you see how this evolves in time. But we couldn't, I mean, also we didn't dare to have a baseline average beauty for all photographers, because we don't really know. Also, people are different, so maybe there are different sizes, etc. So we didn't really want to have an objective measures for everybody. It was really relative to the person. But this is definitely something we could work on. Yeah.